You can get going. Okay. Hold on. I will just if you just give me a minute. Okay, so yeah, I guess we should get started then. Okay, let me get the formalities out of the way. So I want to introduce Luis to I guess people who don't know him. Luis used to be a PhD student here at UCT, but he did his undergrad in Mexico, and yeah, in his PhD he worked on QCD, some rules, and finite temperature QCD. You know, where he was very prolific. You know, published many papers over there, and then proceeded to do a postdoc in Mexico, the National University in Mexico. I think for 3 years over there, and now has is a lecturer in the same city, though a different university now, right? It's the Mexico City University, I guess. Yeah, so he works now on QCD, understanding QCD matter in under extreme temperatures and in the presence of strong magnetic fields. And yeah, and he's done lots of work in this field as well. So we are excited to hear about what he has to tell us today. Okay, Luis, please take it away.
Okay, thanks, Mawande, for the invitation and this kind of introduction. I'm very, very happy to be here, well, online in this seminar. This is the third time that I'm giving a talk in this seminar. That's nice. And today I will talk about the ideas or some concepts to understand the behavior of the strongly interactive matter in extreme conditions. I will try to give you some ideas around this phrase. And exactly, I want to describe the features of this QCD phase diagram, the phase diagram of the quantum chromodynamics, and more in specific, at the end of this talk, I will try to show you what is the meaning of the critical endpoint in this phase diagram and how we can find it, maybe where this critical endpoint is in this phase diagram, right? Okay, if you have any question, doubt, please interrupt me at any time. And I will try to answer your question. Okay, so for the first part of this seminar, because this seminar is divided into parts, the outline of my talk is, well, at the beginning I will try to give some motivation, present some concept, names of some stuff that I will use to describe the QCD phase diagram as a second part of this talk, and the last one is sorry, the second part is the QCD phase transition. I will try to explain how we understand and how we compute and observe this phase transition. At the end, I will summarize everything in the QCD phase diagram, how is our understanding nowadays about this QCD phase diagram, okay? So this is some slides for students. I think everybody knows what is the structure of the standard model of elementary particles, but let me say a few words about this model. Okay, the first part is try to show the pieces that made of this standard model. We have something like a periodic table, like in chemistry, but in this case is made of these most fundamental blocks of visible matter, the matter that we can detect and interact with them. Here in this picture, I have like different set of particles, different colors. For these particles in this ring, in the upper half of this ring, I have this the quarks. Quarks are particles that can interact by the electromagnetism or electrodynamics, and as well as a strong interaction. They have electric charge and color charge, and there are other set of particles that are in this other ring, or half of the ring, in green color, that are leptons. They don't have color charge. They are this tau, mu, muon, electron, and the neutrinos, the three neutrinos, the three flavors, electron neutrino, muon neutrino, tau neutrino. And here in blue color, I show them the bosons, the gauge bosons, that are the particles that carry the information of this interaction, and they are the particles that interchange the information of that interaction. There are five different gauge bosons. The gluon, that is this one. This is the boson gauge for the strong interaction. Here is the photon, that is the boson gauge for the electromagnetic interaction. And these other three bosons, three because there are two W bosons, W plus, W minus, and Z are the other three bosons that they tell us about the weak interaction, right? And in the middle, we have these Higgs bosons that provides some explanation about the masses of these particles, the fermions in this model, that are these quarks and these leptons. As well, the mechanism why this gauge boson, the W, the plus W, the minus W, and Z0 is are massive. Okay, so with all of them, we will try to play a game and understand the fundamental interactions. Okay, so we have four different fundamental interactions. The first one in this picture is the gravity. The second one is the electromagnetism. The third one, the strong interaction, and the last one is the weak interaction. With these three interactions, we can understand what happened in these fundamental levels of understanding of this matter. Actually, gravity is not necessary to take into account when we analyze what happened with the elementary particles, because the strength of the interaction is really small. And honestly, the other reason is because we don't have a theory that describes with success the gravity in the regime of the quantum mechanics, right? Okay, so that is, in a few words, the standard model of elementary particles. And for this talk, I will concentrate all the ideas around this strong interaction. I won't talk about anything about electromagnetism or weak interaction. Okay, so in order to show why we are interested in the understanding of this QCD phase diagram, is because maybe some system shows shows some new phase of the matter. So in that case, the first example that I want to use is the universe. The universe itself. We believe, we are almost convinced that the universe starts with the Big Bang, this explosion, okay, and that the system evolves until nowadays, and now We see our universe at very low temperatures. We see that we have galaxies, stars, around the stars, many objects, planets, etc. But at the beginning, due to the high density, the high energy density of the system, okay, we have a lot of energy in a really small volume. That is a reason to think that maybe the system, the universe in the early stages, was made of this, the matter that we know, but in extreme conditions. When I say the matter that we know is actually nuclear matter, the nuclear matter in an extreme conditions. Well, what is the meaning of these extreme conditions? We can think that, okay, the system is with a lot of energy inside, and one way to see that energy is with the movement of these particles. These particles has a lot of kinetic energy, and if we take the average of the energy of the kinetic energy of these particles, we are able to obtain the temperature of the system, this macroscopic observable. And well, that means that at the beginning of this universe, the temperature was really large. Okay, so in that situation, the question is, well, the matter can be represented with the same degrees of freedom as we represent nowadays. For example, we try to study what happened with an atom. Well, we see that we have some electrons around the nucleus. The nucleus is made of protons and neutrons, that are particles that one can see or detect in our experiments. But we cannot see directly any other kind of particle when we describe this atom. So when we put in extreme conditions, actually, the idea is that we are in the situation where we observe what is inside of that protons, are neutrons or neutrons, because both particles has structure, and now we know that they are made of quarks and gluons. Okay, so the system in the early stage, we think was like a system with quarks and gluons as degrees of freedoms. We call that system the quark-gluon plasma. Okay, so if that happens in the early universe, that means that in the middle, from that stage to nowadays, something happens. Okay, the matter change the degrees of freedom that tell us that occurs phase transition, and that is one motivation to try to understand this QCD phase diagram. Other here this early stage that I call the quark-gluon plasma. Actually, we can understand when we have a system made of some particles and we increase the temperature of this system. Actually, we see that the distance between these particles is shorter, and we can have an almost homogeneous thing, like a macroscopic system, a homogeneous system, but with particles like quarks and gluons that are free interacting among them, but they are actually the real degrees of freedom of our system, not the protons or neutrons or some other particles like pions or baryons and mesons in general. I will talk about these mesons and baryons in a moment. Okay, but okay, that is what we believe is correct. And but that is there is another physical system that we can study and maybe observe more or less the same situation with for different reasons, but more or less the same situation. And that system are the neutron stars. The neutron stars are this latest state of supernova, Okay, and in that case, we believe that inside of that neutron stars in the core, actually, due to the high density as a consequence of the pressure in the gravitational pressure that happens in this star, we have a core maybe made of this quark-gluon plasma, maybe. Okay, this is less clear, these ideas that I try to explain you, but we know that the density of this system is larger than the nuclear density, 2-3 times more larger than the nuclear density, and because we cannot see directly what happened inside of these neutron stars, and we have few observables of this system, we are not convinced that maybe inside of these stars we have that kind of matter. But if that is correct, well, we, in this case, the density of the system is very large. The meaning of this density is that all of these hadrons that can live inside of this neutron star maybe are really close to each other, and as a consequence of the distance, the distance between two hadrons is really small. Actually, the particles inside of that hadrons, think like a bags. Okay, if the bags are really close, the boundaries of that bag disappear. Okay, and at that sense, you can see that the system one more time has the quarks and the gluons as degrees of freedom, because you break or lost the idea of these boundaries that represent these hadrons. Okay, so in this case, it's not as a consequence of the movement of the particles, it's a consequence to put together all of these hadrons in a finite volume. Okay, and there is another system or relevant system that is not the universe of the neutron star, that we cannot manage or has some control over that system. In this case is a system that we can have some control over this experiment. In this case is the relativistic heavy ion collisions. The idea is use these large accelerators and change the beams. Instead of protons, we can try to collide heavy ions, nucleus of heavy atoms. Okay, the idea is if we increase the number of collision in a small region, maybe we are able to obtain as a consequence of the reaction, a medium, okay, that can thermalize, and you can produce at some stage of this collision the quark-gluon plasma. Okay, and well, the reaction start to increase the volume, and the energy density decreases, and some point this quark-gluon plasma that in this plot or picture you can see here, maybe at this stage we have the quark-gluon plasma, but because the density energy of the system decreases, at some point these quarks and gluons start to hadronize, and after some time they the number of particles per species is fixed, and we keep this kinetic fix out, and then particles flies to our detectors, and we see all of these particles like hadrons, photons, electromagnetic proofs, etc. And we collect that information in our detectors and try to reproduce or try to see the whole history from the initial states to the final states, and prove that our theory is correct or not. Okay, but okay, at this point, maybe it's possible. Well, now we are convinced that it's possible to create this quark-gluon plasma. Okay, so this is other system, and the relevance maybe of this system that is that with these relativistic heavy ion collisions, we are able to modify the temperature and the density of our system. That means that maybe we can try to connect or create a bridge between what happened at the early universe and what happened with the neutron stars. Okay, that is possible because if we change the energy of this collision, we can change these two parameters, temperature of or density, and observe different combination of these two variables and try to connect these two systems that I mentioned in the previous slides. Okay. So in order to put together all of these ideas about the systems that I mentioned, and if we have to the same system described by two different degrees of freedom, we try to build a QCD phase diagram. And that means that we try to mapping all the conditions that I mentioned before. For example, if we are observing or studying a system with a really large value of temperature, okay, but small density, which kind of density? In this case, I will talk about the baryonic density, okay, that you can think easily this density as the difference of the baryons and minus and type baryons, okay? And in this condition is like, okay, I can see that that is the condition that I observed in the early universe. On the other hand, if we increase the density of the baryonic density of the system, but we are working at really low temperatures, well, that represents, or that is the same situation of these neutron stars. As I mentioned, the relativistic heavy ion collisions try to explore what happened in the middle. Okay, when we start with protons and neutrons, collide them, we reach this, we obtain as a consequence of the collision the system described in this region as a quark-gluon plasma, and after some time come back to the hadronic world. Okay, so if we have two ways to write or describe our system, one is by hadrons or hadronic matter, and the other one is by quark-gluon plasma. At some point, in some combination of temperatures and densities, we need to observe a phase transition. That in this case is the boundary between these two colors, the red color and the yellow color. Okay, now I don't have any tool to say where exactly is this transition line. I will try to provide some concept or ideas in order to understand how we can identify this phase transition. All right. Okay, at this moment, you have some comments, questions, doubts? Okay, if not, let me continue. When I mention or I say this strong interactive matter is if I have a large number of particles that interact by the strong force, how they behave. Okay, there are two different scenarios. One is when this strong intergalactic matter is made of hadronic matter. What is the meaning of that hadronic matter? Well, we have some degrees of freedom that we call hadrons that actually they have a structure. They have they are made of quarks and gluons. And the recipe, the easiest recipe to define these hadrons, well, we have two kinds of hadrons. One set of hadrons is the mesons, that we understand that meson as some combination of quark and anti-quark. These two elements we call valence quarks. Yeah, I don't remember the name in English. Yeah, we have a combination of quark and anti-quark, and for baryons, we have a combination of three quarks. Okay, the reason why we have these two combinations is because we need to create a system with without colorless. Okay, we know that quarks, gluon have colors, sorry, but this system made of these quarks and gluons, they don't have a color. Okay, there are other combinations that now days we know can exist, tetraquarks, pentaquarks, and some exotic states. But for this talk, let me only talk about the mesons and baryons. Of course, if exist or we have baryons, we have antibaryons as well. That is a combination of three antiquarks. That is the other combination that we will use. But the other phase of this strongly interacting matter is when we describe the system with only quarks and gluons as a degrees of freedom. When we don't need to talk about this meson or baryons, we need only to consider the quarks, the six flavors of quarks, and the gluons. In this case, we have free color charges in our system, and that is why I put this sentence: the two sides of the same of the coin. We depends in which energetic region we are. We describe the system with mesons and baryons, or we describe the system with quarks and gluons. All right. How we connect, or how we know where we are able to describe the system in order in terms of these mesons and baryons, or in terms of these quarks and gluons? Well, the idea that allows to think about these two different scenarios is the one property of the quantum chromodynamics. The quantum chromodynamics has the property of the asymptotic freedom. That property tells us that, okay, if you analyze the strength of the interaction, the strong interaction, well, you need to know that this strength change as a function of the energy. Okay, the energy interchange, or the energy interchange of these two particles that interact in terms of this strong force. Okay, if the energy is large, actually we observe a decreasing behavior of this coupling constant, the strong coupling constant, that tells us the strength of this strong force. Okay, so because decreases as a function of the energy, when this energy is large, the value of this alpha s, that is the coupling constant, decreases and is small. Okay, well, the only way that this alpha s would be equal to 0 is when the energy goes to infinity. Okay, that is why we call asymptotic freedom. It's the quarks and gluons will be, or would be free only when the energy of the system goes to infinity. Okay, but on the other hand, if the energy of the system decreases, okay, we can see that the coupling constant increases, and that tell us that, okay, the strength of the interaction is large, okay? That is why we observe this kind of system, hadrons, baryons, or mesons. They live in their regime where the energy is small or is not large enough to think in terms of quarks-gluons, and the quarks-gluons that are inside of these hadrons will interact with a really large value of alpha s. Okay. Now I'm seeing that this part is in Spanish. Sorry. Okay. But here is the same thing that I mentioned about the properties of this running coupling in the QCD. Okay, so with this behavior, we can identify where we can talk about our system, or where our system is made of hadrons. That means is when the energy is small, and we talk about the quark-gluon plasma when the energy or the typical energy of the system is large. Okay, large compared with what? Okay, there are some value, very important value with that characterize these two regimes, that is lambda QCD. In a moment, I will talk about of this value called lambda QCD. Okay. Well, okay, now this is another cartoon of this QCD phase diagram, where we can see more information. The most important thing here that you can see is, okay, now the boundary between the hadronic matter and the quark-gluon plasma, okay, it has like two different ways to draw this this line. You can see here is without any really boundary, because we know now that the phase transition at really low baryon density is a crossover. Okay, so we represent this a continuous transition of the system from hadrons to the quark-gluon plasma. Okay, as this in this region, but many theoretical results with effective models or some different techniques that we use in order to see what happened at high density. We observe that the phase transition in that systems, when the density is large but temperature is really small, maybe in some cases with the temperature is equal to 0, we observe a different kind of phase transition. Actually, we observe the first order phase transition. Okay, and well, we don't know exactly where that kind of phase transition finish. Okay, but we try to see or try to plot that maybe some region. Okay, we can observe that first order phase transition. We start with a crossover, we finish with a first order phase transition. Well, at some point, okay, the crossover finished and the first order starts. Okay, that specific point is called the critical endpoint. Okay, so now the summary of this picture is that, okay, maybe we need to try to find the critical endpoint in order to see another property or to know another property of this QCD phase diagram. Okay, what else? Yeah, nothing else. Okay. But as I mentioned in the previous slide, that is a cartoon, because actually our current knowledge of this QCD phase diagram is really bad. We know many things when the density of the system is small, okay? In this region, we know very well what happened with the system. How is the phase transition? We have experiments that provides result in that region, more than one experiment. That is good because we have information that we can compare between or among the different experiments. We have many different techniques in the theoretical side to understand the behavior of the matter and how is the phase transition at these early stages. The most important technique from my point of view is lattice QCD that gives us the answer to the question, how is the phase transition at that conditions, these conditions. They found that is a crossover, okay, and many other methods and models and found the same result, okay. But for this region, when the density increases, even if the temperature is large, it doesn't matter that. The important thing is the net variant density. If that net variant density is large, actually, we cannot use lattice QCD. Lattice QCD has a problem with the sign problem. We call the sign problem. We cannot use that technique because the technique that they use fails when the density is finite, because the observables, this is in a few words, because the observables are not real and real, and okay, we have problems with that idea. But there are many new techniques from that side that they try to find what happened at final density with some errors that increases when this density increases, and at least they provide information in a not bad region of this variant density. Okay, so the other reason that why we don't have more information in this region of the phase diagram is because we don't have enough information from the experiments when the density has these large values. I know, no, and many of you know that at RIC, no, with the beam energy scan program in the phase 1, 2, and phase 3, they try to explore with different energies, right? What happened in this region, okay? But the problem is the statistics. I think they don't have enough statistics to find a conclusive information. And in the future, we will have 2 new experiments that try to explore exactly this region, okay? One is FAIR in Germany, and the other one is NICA and in Russia. Okay, both experiments, they have a specific program to study what happened in a system at really large variant density, okay? Well, and now it's time to see how we can identify that some phase transition happens in these systems. Okay, this is the part 1, the first part, when we try to study the restoration of the chiral symmetry. Okay, this analysis is focused on the mass of the quarks. Okay, essentially we try to study what the meaning and the value of the mass when we have the condition of the system. And really, in vacuum, we know very well that okay, the quarks has mass, but they has a dynamical mass. Okay, it's not correct to think that okay, in vacuum I have a quark alone, completely isolated. No, I have a quark and a cloud around this quark made of more quarks, more gluons, okay? And all of this, the information of this system, the quark and the cloud around the quark, provides the information of this dynamical mass. That is around 350 MeVs, okay? That that value has the same magnitude, or is around the same magnitude of this lambda QCD. Lambda QCD is a quantity that appears in the expression of the running coupling, how the strong coupling change as a function of the energy, okay? So this parameter tell us where we are close to the dynamics of these very massive particles, that at the same time, when we works at low energies, actually is the regime where we observe hadrons, okay? But on the other side, if we increase the energy, in this case, I will think that if we increase the temperature, if we work at high temperatures, actually what we see is, okay, this quark, okay, and the cloud start to disappear, the cloud around this quark. The reason is because the energy is increasing and the coupling constant is decreasing. So all the information about the interactions, okay, that is enclosed, or the information is put in this cloud, okay, start to disappear, okay? So at really high temperatures, actually, we will be able to observe the quark isolate, almost isolate. And for that case, the mass of the quark is really small, a few MeVs, okay? I think I must say that when talk about quarks, I'm not talk about any flavor of quarks. I'm thinking in the lightest flavors. That means up, down, and strange, because in that case, these ideas of compare masses in the different regimes make sense, okay? Because actually we can translate this information in terms of compare the masses of hadrons and the quarks that make that hadrons. In case of the lightest quarks, for example, a pion that is made of the quark up and quark down, or combinations between these two flavors, the mass of the pions is around 140 MeVs, but the bare mass of the quarks, okay, is around, in average, 5 MeVs. That it's a huge difference, and in that case we can think about the restoration of the chiral symmetry. Okay, the restoration of the chiral symmetry formally happens when the particle is massless. Okay, so if we compare 5 MeVs with 140 MeVs, we can approximate the mass of the quarks, the bare mass, the mass here, like close to 0 or 0. Okay, and that allows to talk about the restoration of the chiral symmetry. Okay, well, if that restoration happens, actually is because something happened with the symmetries of the system. Okay, we start with a system with the chiral symmetry restored. That means that we have left quarks, right-handed quarks, okay, that are decoupled. These quarks, you can understand this, the meaning of this chirality in terms of the helicity. When the mass is equal to 0, is the same idea, and is the projection of the spin along the momentum of that particle. You have two options. that both vectors are parallel or anti-parallel. If they are parallel, okay, we call that particles right-handed, and if the vectors are anti-parallel, we call left-handed particles. But when the mass is finite of these particles, okay, we break that symmetry, and these two particles, left-handed and right-handed, are coupled one more time, and we finish with a new algebra. Actually, is U and F. V is the vector, and F is the number of flavor, and well, U is spatial and unitary algebra. Okay, and related with any symmetry, and when we try to observe when it's restored or not, we can associate an order parameter in order to understand when the symmetry is broken or is restored. Okay, in other words, is we can see how is the behavior of this order parameter, because with that information we are able to identify when the phase transition happens. That is in terms of statistical mechanics, right? For this chiral symmetry, the order parameter is the chiral condensate, quark anti-quark expectation value. In other words, is the vacuum expectation value of our theory, the QCD, but only in the contribution of the quarks, ignoring or without taking into account the gauge sector. So in this case, that is the order parameter. Okay, we call chiral condensate. But we have another way to try to identify where the phase transition in QCD occurs. This is when we try to identify the deconfinement phenomena. Okay, that we can see in terms of the distance between the hadrons. Let me try to explain a little bit what is the idea. Okay, if we have these hadrons that they are made of quarks and gluons, in this case only I show only the quarks with 3 different colors to show that this system is colorless. Okay, so typically we have some distance for these hadrons. The distance is related with the lambda QCD, that is the scale that tells us where we have the hadronic sector or the quark-gluon plasma. Okay, so typically the distance, is lambda QCD, right? And other variable that we can use is the distance between 2 hadrons. Okay. This part, okay, the distance between the 2 hadrons. Typically, we can measure the distance as a 1/T, the temperature of the system. You can see if we increase the temperature of the system, the distance between 2 hadrons decreases. But that at the ends provides the information of, okay, if we work with high end temperatures, actually the distance between 2 hadrons is less than the size of the hadron. In that sense, you think like you are putting the hadrons really in a small space, and one more time the boundaries, you think like a bag, these hadrons, the boundary of that bag disappears because there are an overlapping phenomena in this system, right? So in that that is the idea how we understand or see the deconfinement phenomenon. Okay, entonces that is related with the temperature when we observe that the distance between the hadrons is 1/T. Okay, if T is more or less the same order of lambda QCD, actually we can start to lose the idea of these boundaries of the hadrons. That is the deconfinement, right? Associated of this analysis, we need to try to build or construct order parameter, okay? In this case, it's not related exactly with a symmetry. That is why this order parameter is not really, well, honestly, I don't like, but because it's not exactly related with a symmetry, but we can, of course, analyze and compute the thermodynamics of our system and try to identify with this parameter the phase transition. In this case, the idea, we need to try to provide a picture how we can understand this or the parameter. In this case, if we have a system, okay, a medium made of these quarks and gluon, and I want to put or one extra quark, okay, I need to take into account the free energy gain in response to this quark, okay? So we have two options, okay? If this free energy, that is FQ, okay? I define that free energy as FQ is equal to infinity, we say, okay, the system is confined, okay? I need infinity energy to put that particle in the system. Actually, one easy way to explain this idea is in vacuum, we need, or low energies, we need a system without a color, okay? If you include one quark, you need to include one extra particle with color. So the change of the system, the system will change as a from colorless with a color, but we can observe nothing with finite color in the nature at low energy. So that is like a condition that is that tell us, okay, you cannot see that phenomena in nature. Okay, so this is why this FQ, the free energy, is equal to infinity. But in the case that is less than infinity, is finite. Okay, this free energy, we are talking about the deconfined region. Okay, in other words, okay, we can take the exponential of this quantity, but all the exponentials need to be without the dimension. Okay, so divide by t, e minus fq over t. If fq is equal to infinity, this exponential is equal to 0. We are in the confined region. But if fq is less than infinity, actually this exponential is larger than 0. Okay, and we are in the deconfined region. We call, or we identify this exponential, okay, as a Polyakov loop. Okay, the definition of the Polyakov loop is this one. Okay, it's is the expression for this order parameter. Okay, so at the end, we have two ways to analyze the phase transition: the chiral symmetry or the deconfinement. We can plot actually the two order parameters in order to see where the phase transition happens. And here I show two plots. The first one, this is the chiral condensate as a function of the temperature. You can see it's finite, start from 1 and start to decreasing, and at some point is really small. Okay, I mentioned that at a finite temperature, low density, 0 density, actually the transition is a crossover. Okay, we observe here that behavior because this function is continuous. Okay, you don't see any discontinuity, no, of this function. Okay, the derivative of this function is continuous in all the range that I plot. Okay, so in the case of analyze the kind of the phase transition, well, in this case is a crossover. We don't identify any discontinuity in this function or in the derivative of this function. Okay, so we see that, or we mentioned that the phase transition happened when the curvature of this curve change. Okay, you can see more or less is around 150 something, 50, we can say like that. And the other plot is the same. In the horizontal axis is the temperature, in the vertical axis is the Polyakov loop. In this case, remember we start from 0. Okay, at really low temperatures is when FQ is equal to infinity, and when increase the temperature, this Polyakov loop increases. Okay, and one more time we observe a change of the curvature around more or less the same value, 150 something or 160. And well, that is a signal of a phase transition, right? Let me say something else. You can see that the region where the phase transition is identified in terms of the chiral symmetry or in terms of the Polyakov loop is more or less the same. That is not strange to think that must be more or less in the same values. And one important thing is that both values of the critical temperature, we call the critical temperature when happens the phase transition, is in around the value of lambda QCD. That is not strange because lambda QCD tells us where we can talk about hadrons and where we can talk about quark-gluon plasma. Okay. All right. Any comment, doubt until this part? All right. Well, this is like an updated version. Actually, it's because I put more sentences here, but it's the same phase diagram that I presented before. Here, I emphasize the critical point or the critical endpoint because, as I mentioned, at low densities, we observe this crossover phase transition. At high densities, we observe, well, not observe, we have many results that tell us that maybe the phase transition is a first order phase transition for the strongly interacting matter. And well, the idea in this decade for the community that try to understand this QCD phase diagram is try to identify or locate where is the critical endpoint. Okay. For that, I will say, or I must say that nowadays we don't have any idea where the critical endpoint is. Here is a table where I show different results with different techniques, with different effective models, and the result for that analysis is that all of this work report is here. The value of the temperature related with this critical endpoint, and then chemical baryonic potential for this critical endpoint. And you can plot if you want, or only read these values and see that are completely different. Okay, they are like points in every place almost of this phase diagram. This is another summary of the results. Is the same plane, the chemical potential in the horizontal axis, the vertical axis is the temperature, and the black diamonds, these ones, okay, are some results of where the critical endpoint is. okay, from different techniques, different groups that shows that result. And well, looks like, okay, if somebody says that it's here and somebody else says that it's here, the difference is huge. Okay, actually, that is the current situation. We don't have exactly idea where is. Okay, maybe we know that the critical endpoint is not close to the vertical axis because we have enough information to discard that ideas, but when we try to see what happened in this deep region, actually we don't have any idea. That is the truth. Well, in order to identify now the critical endpoint, we learn how to identify the phase transition where the system changed from hadron to the quark-gluon plasma. Now I will try to provide some ideas about how we can identify the critical endpoint, this point where we can see the change of the phase transition from crossover to first order phase transition or vice versa. Okay. Well, the idea is try to understand the fluctuations of conserved quantities. In this case, we try to study what happened in heavy ion collisions. As I remember, as you remember, at the beginning of this talk, I mentioned that these heavy ion collisions try to map what happened in different combination of temperature and density. Okay, that is because we can change the energy of the collision and try to see what happened in different regions of temperature and densities. Well, we try to analyze the fluctuation of conserved quantities. What kind of conserved quantities? The density of charge, the density of number of baryons, strangeness, many other conserved quantities. How we can try to analyze these fluctuations? Well, we try to analyze in the experiments what happened event by event in these collisions. Okay, we try to see the fluctuations through this event by event analysis. Okay, the fluctuations are sensitive to the early thermal properties. That is important to emphasize the thermal properties of this medium created as a consequence of the collision. And in particular, the idea is try to see the possibility to detect non-Gaussian fluctuations in conserved charges. Okay, that is the key. Try to see if when we have the value of some conserved quantity in one event and we repeat the same experiment, okay, one more time and another time, and I don't know, a million times we repeat this experiment in the same conditions, we try to see how is the distribution of this value, okay? And the idea is try to see if the distribution is different from this Gaussian distribution. Why? Because the critical phenomena show tell us that, okay, the correlation between the correlation length in this system increases. That means that the distribution is like change the shape, okay, and you have a large dispersion around the mean value. So we observe this new distribution really different or far away from this Gaussian distribution. Okay, so that is the idea of these fluctuations. Try to observe these fluctuations. In this case, the idea is the following. Let nx, the function nx, be
I'm sorry,
the
Luis, can I ask a
yes,
question?
yes, sure.
Super. Yeah, this second point that you've pointed out is something that I've been wanting to understand better for a long time. And I'm curious about both comments that you have there. First, that fluctuations are sensitive to the early thermal properties, and I'm curious to what extent those early time fluctuations are or are not going to be flooded by any kind of late time evolution fluctuations. And then probably more importantly, could you talk more about this non-Gaussian fluctuation? So you said, okay, I have a correlation length that is changing. So if I'm at, say, a second order phase transition, my correlation length goes to infinity. But that's a comment about spatial correlations. And when you say non-Gaussian fluctuations, I'm thinking here it's like, okay, how many protons do I see? And I see, you know, 1 million times I see 10 protons, and then 10 million times I see 11 protons, and so on and so forth. And I create a histogram of the number of protons, number of times I see the number of protons, for example. So is that what you mean when you say non-Gaussian fluctuations? And if so, how does that connect to the correlation length? Thank you.
Yes, thanks, Will, for the question. For the last part of your question, yes, the idea is not exactly related with the spatial correlation. It's related with the, for example, if we try to measure the number of protons, okay, we expect if we repeat and repeat and repeat the experiment, more or less a systematic behavior. That okay, if we observe 100 protons, maybe the next time I observe 122, the next time some other value around this value, and we observe maybe a peak, okay, and the dispersion is not really large, okay. But when we observe a critical behavior, that maybe we need to talk about what happened, what is the meaning of criticality in terms of these statistical mechanics. But we actually observe that exists a really important contribution from these values far from the central value. Okay, so the distribution start to spread like a wide distribution, and we maybe observe in this observable the number of protons that at some time we observe 10,000 of protons in one measure. It's like crazy number, okay? But the example is like that I try to put on the table is we observe really significant difference when we measure one more time the same the same situation of the experiment, and the observable provide different numbers. That is why we expect a non-Gaussian distribution, because the tails start to tell us something about the system. It's clear my answer?
I really like your comment about how this distribution broadens as you get closer to criticality. That makes a lot of sense to me in an intuitive level, that you have just crazy fluctuations happening in the system. And so then you have that imprinted on this distribution. So then what is it that means that those fluctuations will yield that are non-Gaussian? I guess it's some kind of like power law tails. Is that what one is looking for?
No, actually, maybe the next slide probably will provide a better information. Actually, we try to see, for example, what happened with the not only the first and second statistical moment, what happened with the third, fourth, fifth order momentum in this distribution, because we see if the distribution it has like some asymmetry, or if the distribution is like here it's like with the cortices we try to see if the distribution is less sharp or not. That is why we try to see with the momentums of this distribution, try to observe how far we are from this Gaussian.
Yeah, so I definitely see that, yeah, skewness and kurtosis are going to measure how far away you are from Gaussian. Yeah, I still don't quite see why criticality leads to non-Gaussian fluctuations, but maybe let me let you go and we can talk more at the end or offline.
All right. Yeah, if not, maybe for the next week, let me prepare some slides to try to explain maybe in other contexts when we try to see this. If I don't pronounce very well the name, tell me. The opalescence phenomena that happens in a system, for example. No?
Yeah, critical opalescence, yes.
Exactly, critical opalescence. Maybe I will try with some slides explain why it is important to understand these moments in the distribution.
Oh, okay. So yeah, Luis. Yeah,
Yeah.
I have a question, but you know, we also, I guess we're running over time a little bit.
Yeah.
Yeah. So so
I don't know.
when you're running these experiments, you imagine what you keep dialing up the energy of a collision and then measuring these fluctuations and then
Yeah.
dialing up the energy again and then measuring the you know.
You keep the energy of the collision, the same species of these heavy ions. Try to keep the same conditions and repeat this experiment. Actually, is the how works that experiment. At the end, we report what happened after many measurements of the same observable. Okay, in this case, is try to build this distribution of one observable, not any observable, is some conserved quantity. The charge density, for example, is one, other is the baryonic number of particles. Okay, maybe we can translate that idea in terms of how many protons we observe in our detectors as a consequence of the collision, and see how the change that number that we observe. Okay.
Yeah, but okay, yeah, but well, then suppose you do that measurement and you find like your non-Gaussian fluctuations. Okay, what information can you draw from there about where the critical endpoint is? Like what temperature and you know, what temperature and what mu b your critical. I don't know. Are you trying to find the critical endpoint or the kind of like the phase transition line?
No. The phase transition line, we can analyze that system in a different way. Okay. As you know, we know the information at the beginning of the collision. We know the initial state. We try to collect all the information after the particles arrive to our detectors, right? And we try to tell what happened inside. Okay. And there are many observables that we can provide more or less or with some accuracy, the value of this critical temperature, and that we can use that information. But in this case, the phase transition happens, but we need to add the information that, okay, where we observe this phenomena of criticality, because it's in only one point in this phase diagram that we can observe that phenomenon. Not in any other place or any other region or value of along this phase transition line. It's only in one place. So in other region, we are not able, or we expect, don't observe any non-Gaussian fluctuation. Okay.
Okay. Thanks.
Yeah. Actually, you mentioned about the time. Look, one thing that we can do is, if I stop here and I start to talk about one more time about fluctuation for the next time, as you can see, it's like a few slides, 5 or 6 slides, but I will try to answer both questions, the question that Will did and your question, using maybe some other example, and I try to continue to explain what happened with these fluctuations and how we try to identify the critical endpoint. What do you think?
Yeah, that's fine with me. So you're saying this is a good stopping point?
Yes, I think, and we will continue with the fluctuations next week, and I will try to show with a simple model, the linear sigma model, how we can observe this critical endpoint. All right.
Okay. Well then, yeah. Thank you then, Luis, for the very nice talk. Yeah, I guess now the floor is open for any questions, please. Any more questions for Luis?
Well, if the students maybe are shy, look here, you can find my emails. You can send me your questions by email if you prefer, and I will try to answer your question next week.
Sorry,
Daniel.
I had one question, but I
Sure.
think it only kind of dawned on me that I didn't quite understand it a few minutes ago. When you spoke about the mass of the quarks quite a bit ago, at low temperature, they had these very high masses. And then as you increase the temperature, they lost their cloud and had very low masses. And then on the next slide, you talked about oh, sorry, not the next slide. I think a few after this slide. Yes, the temperature, the deconfinement at high temperatures. Are these two the same phenomenon, or are they stemming from the same phenomenon?
They try to explain the same ideas, why we can change from hadrons to quarks and gluon as a degree of freedom. In the first part here, no, the first idea is try to analyze what happened with the chiral symmetry. Maybe I need to say a little more information about this symmetry, but the most important thing is that the symmetry is related with the mass of the particles. We try to identify when the particle is massless and when this has mass. And with that idea, we can identify when the chiral symmetry is restored and when the chiral symmetry is broken, respectively. So this idea is completely related with the mass. Okay, we analyze what happened with the mass of these quarks. Okay, and with that analysis, we are able to observe when a symmetry is broken or not. Okay, the other idea is no. Now, instead of analyze what happened with the mass, we need to see what happened with in this case, in this really naive explanation, the idea is to see how the temperatures modify the distance between two hadrons. Okay, I start with the hadronic matter, and I will try to describe what happened with the system when the temperature increases. Well, I can see that if the temperature increases, the kinetic energy of these bags increases. They have the enough energy to decrease the distance between them, that I can compute or tell the average distance between these two hadrons as a 1/t, okay? And at some point, if T is large enough, well, the size of these hadrons and the distance between two hadrons is more or less the same, okay? And in that case, we lost the idea that they are two bags, okay? They are like a system with the same distribution of quarks, more or less. We lost the idea of these boundaries that contains the quarks inside, okay? So in this idea of the confinement is how we try to naively understand the phenomenon, right?
Okay, yeah, that makes sense. Thank you.
All right.
Okay, so Will has a question. Go ahead, Will, please.
Oh, no. I just thought I saw Gibran raising a hand at some point.
No, it wasn't a raised hand. I've got no questions.
So, yeah, so okay, in that case, I'd want to, yeah, just get some more clarification on how, yeah, on how one goes about finding this critical endpoint.
Yeah. For the next time, I will try to give a better explanation for that. I will use maybe another example to show why it's important and why these ideas works in order to find where is the critical endpoint.
Okay, so fair enough. Okay, so it looks like we have no more questions. In that case, thank you, Luis, for the nice talk, and thank you everyone for showing up. Yeah, hopefully next week we can get a bigger crowd.
Okay.
All right. Yeah. Thanks very much.
See you
Thanks
next
to me as well.
Thank you.
Thanks for everybody showing up.
Thank you. That was really great. See you
Thank
folks
you.
next week.
Bye.
See you next week. Absolutely. Cheers.
Cheers.
Bye.
Bye.